Okay, good afternoon, everybody. So the technical part of the course, we're starting by talking a little bit. So we'll spend a few weeks talking about this thing that's called AI, even though it's not really AI, in video games. All right, so far, I guess in the first week of the course and in your first reading that hopefully you've completed or are completing, you've seen that in a modern game, typically it's made up of a bunch of components, which can include things like data structures, right? You'll see that eventually in the course we'll talk about certain algorithms that are common across many types of video games, right? And many types of different software components or architectures that make it easier to implement a modern game, right? Because many modern games, when you think about it, modern games typically have some common set of things that can be reused across different types of games, right? And AI is one of those things, right? So for example, a game engine will typically provide you with some kind of rendering engine, right? That rendering engine has many subcomponents. If you've been reading if you did the first reading, you'll know that a modern rendering engine has lots of different components in it, right? And that saves the game developer from having to deal with, how do I draw stuff on the screen, right? The sound engine saves the game developer from having to figure out, okay, how do I make this sound appear as though it's occurring in the back corner of the room in my game, right? And then finally, you might have a data structure like a scene graph that makes it easier to draw and move things in your world. Right? And so the AI part of a modern game typically handles the common AI tasks, right? And so the next slide's better for this description here. So it's called AI. It's not really AI or machine learning in any real sense. It's called AI because that just happens to be a handy name to give it. But in game AI, typically what's involved is how do you move stuff around in your world more or less without having to script every motion yourself, right? So if you can imagine you have a game, it's got lots of NPC characters in it. You want them to be moving around the world somehow, right? How do you make them move throughout the world in a semi-realistic way, right, without actually having to program every individual character on your own? Right? And so Unity as a game engine, at least when this slide was created, didn't have a whole lot of built-in support for AI, but of course Unity is an extensible engine, so you can find lots and lots of assets that help you with game AI, right? And the same is true of every other modern game engine, right? So Unreal, for example, you can find all sorts of Unreal plugins that help you do AI in an Unreal-based game. Right? So our class, this course basically focuses on some algorithms. The second assignment, and a little bit of the first assignment when it comes out, will have you doing a little bit of this, playing around with these algorithms. The second one, of course, you'll be doing in Unity. The first one, you'll be doing a little bit of Java. The first assignment should come out by the end of this week. All right, so there's this little picture here is trying to show you a hierarchy of tasks that are typically involved or typically use what game developers call AI. Right, so starting at the bottom, these are low-level tasks, right? So steering, which is what we're going to talk a little bit about today. Right, steering is basically local pathing. So you have an object that's moving around the world. You need to figure out when you take your next step, where does the object go in the world, right? So this involves things like detecting collisions with other entities, right? If you have multiple objects that belong to a group, say typically a group of animals, right, or a group of people, or something like that, right? You might have this sort of flocking behavior where they move as a group, right? So how do you get this group to locally move as one cohesive unit, right? If your game involves the player trying to hunt down some other thing in the world, right? That other thing might be trying to get away from the player, right? And so that's evasion. Similarly, if your game involves things trying to hunt the player, right, that involves chasing. So how do you implement this chasing behavior in an easy way, right? So that's the lowest level stuff. This is all local, we call it local pathing. Right? At the level above, there's a harder or a different kind of problem, and so this is the pathing problems. So the pathing problems involve how do you move this thing from point A to point B in the world, right? And so you might have you might need to move some object across your game map, right? And your game map has obstacles and things in the world that might try to impede the thing that's moving, right? So how do you even find a path that gets you across the world, right, from A to B, right? And I guess in a week or towards the end of this week, we'll start to look at these kinds of algorithms, right? These pathing algorithms. A star is the one that's used. A star is the most commonly known one. It turns out there are many more modern variations of A star that work a lot better than A star. But they're more efficient than A star. Right? The level above that is called activity, right? And so in activity, you have an object that's performing some kind of task, right? It's in some sort of mode. So let's look at Pac-Man. So Pac-Man was a game that came out, when did it come out? In the 1980, right? I think I'm assuming most of you have seen or at least have heard of Pac-Man, right? So the goal in Pac-Man, you are Pac-Man, this yellow blob here, and you're moving through this, you're trying to move through this maze, and these ghosts are hunting you, right? And so right now in this mode, the ghosts are hunting the player, right? So they're in some sort of hunting mode. And then when you eat the power-up pill, they're now trying to run away from you. So they're now in the evasion type of motion. Oops, I'm not very good at this, sorry. All right. Right, and so the ghosts, when they are in this hunting and evasion mode, right, they're in these different types of activities. So they need to have some way of planning, how do I get away from the player, right? Or how do I chase the player? And so depending on the complexity of your game, right, the activity unit of the AI hierarchy, your activity planner will figure out some course of action to take, right? That course of action will then go to the pathing part, right? So your activity planner will say, hey, you have to go over here, right? And so the pathing algorithms or unit will now figure out, okay, so how do I get from there to this point that the activity unit wants me to go, right? And then as you're moving or following the path, right, you're asking the steering AI component to figure out how do you actually move from point A to point B, right? So how do you actually do the movement, right? What is the route that I need to take, right? Why am I taking this route, right? And then finally, planning is yet another level above that. It's typically quite hard to do. So planning involves, in the Pac-Man game, for example, Pac-Man would be a lot more, well, arguably a lot more interesting and a lot less interesting, right, if the ghosts were coordinated in some way, right? In the original version of Pac-Man, the ghosts all act independently. They don't know what each ghost is doing. But you can imagine if you had an overall planner that said, hey, these ghosts need to capture the player, what is the best, or what strategy should the ghosts take in a coordinated fashion to hunt down the player, right? I'm pretty sure if you actually did that in Pac-Man, the player would never win, right? You would never clear a level. It's probably the case that the ghost would always catch the player relatively quickly, which is a bad thing for Pac-Man because Pac-Man came out in the 1980s, right? The model for video games in the 1980s was you would have to go to an arcade, drop a quarter into the machine to play the game, right? If you made the AI very hard for Pac-Man, people would not be playing the game for very long, and you wouldn't make any money in that case, right? On the other hand, it might be really interesting to see what happens if the ghosts, at least now, where you can run this on your own computer for free, what would happen if you had coordinated ghosts, right? How hard would it be? It'd probably be very hard, right? And so planning is the level yet above, right? You are planning some sort of high-level task to achieve some goal, right? And you can keep on stacking these on top of one another, right? And so to achieve this goal, I need to achieve some other goal, which requires some other goal, and so on and so on and so forth. Right? And so the difficulty of the problem that you're trying to solve increases as you go up this hierarchy. Right? We're probably not going to look so much at the planning phase here. But steering and pathing and some activity stuff we'll definitely look at in this course. Right? And so today we want to start at the bottom. We want to look at steering. Right? And so steering, here's a little quote here. The ability of an autonomous character to navigate around the world in a lifelike and improvisational manner. Right? Improvisational here is important. Right? You don't want to have to code the motion of these types of things yourself. Right? It would be nice if you can just set them free and they do something. Right? So this is this video doesn't play in PowerPoint, but I do have it here. So here. All right. Okay, so this is an older game called Age of Empires, right? And you can see that there are these people walking around the world, right? And so notice that when they're walking throughout the world, they're not crashing into anything, so that's good. They're not walking through the fountain, for example, right? But if you look closely, they're not really doing anything that looks sensible either, right? They really look like they're just sort of randomly walking through the world, right? In particular, this woman here is just walking back and forth. She's going to turn around and, right? So you want to provide the illusion that your characters are doing something interesting, right? You're not necessarily trying to make them do something interesting, right? When you take computer graphics, you'll learn that computer graphics is all about faking stuff. Right? You never actually try to do the thing you're trying to do. Turns out it's very hard to do. Right? Similarly, adding agency to each one of these non-playing characters is quite hard to do. Okay, so for steering, we're interested in things like, how do I move from point A to point B? Right? How do I avoid obstacles? Right? If you are chasing or trying to evade or get away from something, what kinds of motions, or how do you plan those kinds of motions? Right? And flocking, that's going to be that's the subject of this week's reading. So I've given you one of the original papers that talk about how can you implement flocking, flocking-like behavior for things like fish or birds or herds of animals, not necessarily in a game, but in general. Right? And so you're going to see one of the very, very early papers, 1986, I think, or something like that, that describes how you can implement this in software. Right. And so when you read this paper, keep in mind that this was written by someone either doing a PhD or who has a PhD. Right. If you go online, you can easily find implementations of this by YouTubers in like 15 minutes. Right. This was someone's 3 or 4 or 5 years of work to do. So what you can do today is dramatically different than what you could do even 20 or 30 or 40 years ago. Right? It's really funny going back and reading the early graphics papers, because stuff we teach you in like 20 minutes in a lecture basically formed to the basis of their PhD. Right? Okay, so basic motion. All right, so we're going to do 2D. Of course, you can do this in 3D as well. You just add an extra coordinate, but it's easier to draw stuff in 2D. Right. Okay, so I've got this object. It doesn't matter what this is. It kind of looks like a, I don't know, like a two-wheeled robot or something like that. It could be anything, right? It could be a person, it could be an animal, anything, right? So we're going to assume that this object is characterized by its position in the world, right? So it has a position P, right, in the world. So here I've got the world coordinate frames, right? It's just it's just your X and Y coordinates. Right? So this is on a Cartesian grid. Its location is given by 2 coordinates, right? Px and Py. So it's X coordinate and its Y coordinate in the world. Right? And this particular thing is moving in the direction of that red arrow. Right? So that red arrow is its velocity vector, right? Which it also has 2 components, right? Vx and Vy. Again, those are the components of the vector in the world. Right? So your position, P, the units on its coordinates are some sort of distance unit. Right? It could be in centimeters, it could be in meters, it could be in kilometers, it could be unitless, right? So when you make your, when you are plotting out, for your coordinate system in your game, you might just be talking about units 1, 2, 3, 4, 5, 6, 7, 8. They don't necessarily correspond to actual meters, kilometers, centimeters, or things like that, right? But you have some sort of coordinate system. Right? Conceptually, position is measured, the units of position are in some sort of distance unit. Right? Your vector v, its components are in some sort of speed unit. Right? And so vx and vy, these might have units in meters per second, centimeters per second, kilometers per hour, something like that. Again, it depends on your game. Right? It could be unitless as well, right? So units per second instead, right? Instead of meters per second. Okay, so after t units of time, right, assuming that the object doesn't change its direction, right, its position will have moved. Right? So after t seconds, right, the new position of your object becomes the original position plus the velocity times time. Right? If the object is changing its speed, so if it has an acceleration component, right, you would add that in as well, right? That would be its acceleration times t squared. Right? Now, so the way modern games work is that the amount of time for every frame is very small, right? So 30 frames per second or 60 frames per second. So your amount of time t is 1 over 30 or 1 over 60, which is very small, right? So when you square t, that value becomes even smaller, and then when you multiply it by the acceleration, it turns out the acceleration doesn't contribute very much to the displacement of the object. So often, in video games, they will simplify p plus vt times plus the acceleration times time squared and just drop the acceleration component, right? Unless you want things to fall out of the sky or something like that in a realistic way. And then you have to account for the acceleration due to gravity, and now you need to do some other stuff. But that's a separate story, right? So we're only going to consider the velocity. You might have to consider the acceleration in some circumstances. Right? So after 1 second, right, if you use this picture here, so there's my velocity vector v, right? That point moves to the end of the arrow, right? And so that point moves to here, and now your object has this position after 1 second, right? And you can use that equation directly in your game loop. So for example, in Unity, every object has an update function. If everything's moving in a straight line, right, you can basically implement that equation right there and update the position of the object. Right? Now, instead of using a velocity vector, you might decompose the velocity vector into 2 separate components. You might use a direction vector d, and a scalar speed s, right? So s would be, say, 10 meters per second, right? Your vector d now simply encodes what direction is the object moving in, right? So here I'm showing it as a smaller version of v. It might be the opposite case. If v is small, then d would be a longer version of v, right? But the idea here is that your vector d has unit magnitude, right? So its length of that vector is 1, right? To get the velocity vector, you just multiply it by the speed of the object, which is s, right? And so your velocity vector v, you can think of as being some speed multiplied by the direction that the object is moving in. Right? So the direction vector d is just a unit vector pointing in the same direction as the velocity vector v. If you've somehow gotten a hold of Nick's old slides, his next line is wrong. The units of d are, there are no units on its components, right? Its components are unitless, right? And that's because the units belong to the speed s. S has units of meters per second, right? When you multiply that into the components can't have any units, otherwise your velocity vector has the wrong units, right? So the components of your direction vector are unitless. It's simply the direction that the object is pointed in. Right? So s is the speed of the object. Of course, it's in speed units, so meters per second, kilometers per hour, whatever. Okay, so it looks like we're going to have to do a little bit of math to move stuff around, and that's true. You do need to know a little bit of math in this course. You need to know more math in the graphics course, right? You need to remember how do you compute the length of a vector, right? So the two-dimensional length, or the 2 norm of a vector, you take the components, you square them, add them, take its square root, right? So the length of a vector is often written as, looks like the absolute value of, in this case, A, right? In this case, it's actually the 2 norm. You might also see it written as like that, right? And if you've done any math, you'll know that these are all norms. If you haven't done any math courses, don't worry about it, it's not important, right? So that's how you compute the length of a vector. If it's 3 dimensions, it's just plus az squared, take the square root, right? And that's the length of a 3-dimensional vector. Unit vectors are just vectors whose length are 1, right? So if someone gives you an arbitrary vector A, you can always normalize the vector to get the unit vector corresponding to, pointing in the same direction as A, right? So if someone gives you a vector A and they ask you, hey, give me the unit vector pointing in the same direction as A, you just take the components of A, AX and AY, right? And divide them by the length of A, right? And that produces a vector whose length is 1, right? So that process is called normalizing the vector, or the norm of the vector, or computing the unit vector corresponding to A, right? They all mean the same thing. Unit vectors are used all over the place in graphics, right? So if you take 454, you're going to see them all over the place. Okay, so we're talking about velocity and direction vectors. So if you have a velocity vector and you want to decompose it into a speed and into a direction vector, right? The speed is easy. You just take the length of v, right? And the unit vector is easy. You just normalize v, right? So take v divided by s, and away you go, right? So nothing terribly difficult here. So that's great. So if something's moving in a straight line, it's pretty easy to move it in a straight line, right? It turns out that the displacement of the object is just what we call a translation. Moving things in a straight line is great, but it might be nice if you could turn something as well. So if you wanted to turn something, we call that rotation, right? So far, all that we've talked about is something moving in a straight line, right? If you want to change its direction, you could just move things in a straight line, right? So if you wanted to turn, if you wanted to make it go around a corner, right? Instead of moving in a smooth arc, you could just turn and then take straight lines, right? So everything becomes this sequence of straight line steps, right? So if you want to take into account what direction the object is pointing in as well, right, then you need an extra piece of information, right? So not only do I need the position of the object, I need to know what direction is it facing in the world. So in 2D, right, it's sufficient to specify an angle of rotation theta, right? And so there should be a picture here, but it's not. Well, it might show up later on. So let me just quickly check. Okay, it's going to show up later on. And I am calling it theta, right? Hopefully I don't change somewhere else. Nick called it R, which is strange. It's theta. Okay, so here's the picture. So here's my object, right? Its location is given by P, right? And if you want to deal with rotation, you're going to want to keep track of what's called its heading, theta. So the heading is the angle that the object is pointed in, right? And the way that you measure the heading, right, x, y, right? So the heading is always measured relative to the world's x-axis, right? So it's always measured counterclockwise. So it's always that angle there, right? If you have an angle down here, right? So if your object is pointing that way, right? You can either specify this as the angle like that, right? Or you can say it's some negative value. So in this case, it might be negative 45 degrees, right? But it's always measured with respect to the x-axis in a counterclockwise fashion, right? Counterclockwise angles are positive, clockwise angles are negative, right? And hopefully they taught you that in your first year math courses. If they didn't, that's the convention we're taking here. It's the convention they'll be using in 454, right? This combination of position plus angle in 2D is called the pose of the object. I never see it called pose in graphics. But if you do robotics, if you were to take a robotics course, a mobile robotics course, everything that I talk about here, you would also see in mobile robotics. And in robotics, it's called the pose, right? Position plus its orientation, right? So if you're talking about something having an orientation so it can turn, right, not only does it have a linear speed, right, it now also has an angular speed as well, right? So it can rotate about its position, right? And so its turning speed is called omega, and that's called the angular speed or the angular velocity, right? It's just how fast it turns about its location point P, right? And that'll be measured in degrees per second. If you're in robotics, it would be radians per second, right? But in games, it's often easier to think about the angle in degrees rather than in radians, right? Okay, so how are we going to use the orientation or the heading of our object, right? And so one of the basic tasks that you have to solve in the in steering is you know where your object is, you know what direction it's facing in, and you know where do you want to move the object to, right? So suppose I want to move my object to some position in the world W, right? It's called W for short for waypoint. A lot of pathing problems boil down to computing a set of waypoints and then moving the object from its starting position to the first waypoint, to the second waypoint, to the third waypoint, and so on, and so on, and so forth. Right? Okay, so I want to move to this position W. So how do I actually compute how to do this movement? Right? And so all that we know how to do is turn in place and walk forward. Right? So to solve this problem, you take your object, you turn it in place until it's pointing towards the waypoint, and now you move the object forward until you reach the waypoint. Right? So for example, I wanted to reach the back corner of the room and I'm currently facing this way and this wasn't in the way, right? I would turn this way and then walk towards the, to the waypoint. Right? Now obviously this type of motion is not appropriate for every object that you would want, right? Cars can't move this way, right? Cars can't rotate in place. So if you're implementing Grand Theft Auto, right, you have to have a different way of moving your cars. Right? Bicycles also can't do this. Various other types of vehicles can't move this sort of way. Right? And so for realistic vehicular motion, it becomes a much more complicated problem. Okay, so here's the idea. Here's my object, right? It's facing this way in the world, so its heading is theta, right? Its position is P. I would like to move to W. Right? So step one, I want to turn to face the waypoint. Right? And so what I really need to do is I need to figure out what is the new heading of the object. Right? So the new heading is going to be theta. Right? So it's going to be the angle from the dotted line measured towards the solid black line. Right? So that's the direction I want to make the object point in. Right? And so the question is how do I find this angle phi? Right? And so the answer is it's just SOHCAHTOA. Right? So remember, SOHCAHTOA says that the tangent of an angle is just the length of the opposite side divided by the length of the adjacent side if you have a right angle triangle. So here's my right angle triangle. Right? That's the opposite side. That's the adjacent side on the angle. So the tan of theta is the length of this side divided by the length of that side. Right? So what's the length of this side? Well, if you have a right-handed coordinate system, right, the length of this side, right, is just the coordinates, is just the y coordinate of W minus the y coordinate of P. Right? So that length there is just wy minus py. So there's my opposite side up there. Right? What is the length of the adjacent side? Right? Well, that's just this length here. Right? So that's wx, right, minus px. Right? And that gives you that length. That gives you that value there. Right? Now I'm talking about length, but really these are signed lengths. Right? So these are signed quantities. So this difference here and this difference here can be positive or negative. Right? And so that's the tan of your angle. To extract the actual angle phi, you take the arctan. Right? But this is always a complicating factor. Right? You can't just take the regular arctan of the angle. Right? You have to take into account what direction is this line from here to here actually pointing in. Right? Because remember, tan is cyclical. Right? You can have the tan of an angle can have the same value, but the angle, sorry, two values of tan phi. There are two values of phi which satisfy a given value for a tangent. Right? So if you remember all the way back to your calculus class, tan, cosine, sine, these things are all cyclical, right? And so to compute the correct value of phi, you need to take into account what direction is this thing actually pointing in, right? Every mathematical library has a function called arctan2 that does that for you, right? It looks at the sine of wy minus py and the sine of wx minus px and determines which angle you actually want. Right? Now, every mathematical library also has an atan function, right? Whatever you do, don't call the atan function because it will give you the wrong answer half the time. Right? So don't do that. It will give you the answer you don't want half the time. Right? So make sure you call arctan2. Again, if you have Nick's old slides, the math is dubious in the old slides. I'll just leave it at that. This is the correct way to do it. Right? So that gives you your new heading phi. Okay, so now the question is how do I turn the robot, or how do I turn the object so it's actually facing in the direction given by phi now? Right. Anybody have any questions about this slide? Now's the time. Sorry, now's the time to ask if you have any questions or don't. Yes. Right away. Arctan2. There's an arctan, ATN, and there's also an arctan2. Arctan2 is the four-quadrant arctan function. It figures out which of the two values of phi you actually want. Yeah. I forget what arctan on its own does. I can't remember what it does. It always returns, arctan will always return the angle between some value and some other value. Arctan2 will return the full, will return a value somewhere in the full 360 degrees. Okay, so how much do I actually have to turn this thing by, right? So the total amount of rotation that I need to turn this object by, so the first thing I need to do is I need to turn it by minus theta degrees, right? So if I turn this thing by minus theta degrees, it's now pointing straight to the right, right? So I turn it by minus theta, so its heading is now 0 degrees, right? It's pointing straight to the right. Right? And now I need to make it point in its new heading phi. Right? So now I add phi to that angle. Right? So the total amount of rotation is minus theta plus phi. Right? This picture here shows the angle below the x-axis, but it's the exact same picture, if the waypoint were to be up here. Right? Everything's exactly the same. Right? And in that case, this formula makes a little more sense, right? I turn this way so that it's pointing to the right, and then I turn this way so that it's pointing in the direction given by phi, right? Here it's the exact same thing. It's just that phi is negative here. So I rotate this way, right? Then I add a negative angle, and I rotate this way, and it's now pointing in this direction here, right? So the minus theta is so that the object is pointing to the right. The plus phi is so that it's pointing in the direction, the direction towards the waypoint. Right? Again, if you were to take a mobile robotics, introduction to mobile robotics, this is one of the first things they'll teach you. Right? So all of the stuff you're learning here applies equally to robotics. Everything that you do in graphics also applies to graphics as well. Right? Applies more towards the type of robotics where you have a stationary robotic arm. But it's all the same, it's all the exact same material. Right, okay, so how do you actually do this movement in your game? Remember, you have a game loop, right? In your game loop, you're updating the position of the object however fast your game loop runs, right? 30 times a second, 60 times a second, whatever you have it set to, right? So you've got a couple of choices here, right? If you don't care that the turning is smooth, so if you're willing to live with an instantaneous turn, right? Just set the heading of the object to phi and away you go. Right, so that's an instantaneous rotation. Many games will do that, especially if the angles are small, right? It doesn't really matter if you quickly turn a small amount, right? If the angles are large and you want nicer looking rotations, right, you have to take into account how fast can your object turn, right? So remember this omega term, it's angular speed, back here, right? Back here. Right? So if your object has a maximum angular speed that it can turn by, you're going to want to turn using that speed, or at that speed, sorry. Right? So in other words, however long your frame lasts for, right, that's your t, right? Simply multiply that by omega, and that gives you the amount of rotation. Right? If that term is positive, that's a counterclockwise rotation, right? So we're going this way. If it's positive, right? It's negative. If you have to turn the other way, you're going to do minus t times omega, right? And that'll go the other way, right? And you keep on doing that until your new heading. So every frame, you take a step of plus or minus t omega until you reach your new heading, right? Of course, in your last step, you're probably not going to turn by exactly t omega. You're going to turn by less than t omega, right? So that you end up with your final angle phi. All right, so that's great. We just got step one. I can now point at my waypoint. So now I have to, oh, sorry, question, yes?
Can I ask, is there acceleration for turn speed?
There is if you want it to, but again, you have to remember that in a typical game, t is small, right? So 1 over 30, 1 over 60, 1 over 100. When you square that amount, because when you account for acceleration, you square the time, if you remember your first year physics, right? So when you square a small number, it becomes even smaller. And so when you multiply it by the acceleration, unless the acceleration is very large, it really doesn't contribute to the overall sum. So many games will simply ignore the acceleration. If you want it to be very realistic though, especially if stuff's falling out of the sky, you do have to account for acceleration. Okay, so what about moving to the waypoint? So I'm now facing the waypoint, I now have to move to it, but moving's easy, right? You just multiply your velocity by t, right? And then add that to your current position. So now you keep on doing that, right? In the game loop, so over and over and over again until you reach the waypoint, right? How do you know you've reached the waypoint? You know how far you have to go, right? The distance you have to travel is just w minus p, right? So remember, w is the point you're going to, p was your starting point, right? How far do you have to go? Well, you just take the length of that vector, right? W minus p, right? And you just keep track of how far you've moved until you've actually moved far enough to reach the waypoint. Right? And so moving to the waypoint is relatively straightforward. You're just taking steps along in the same direction until you get to the waypoint itself. Oh, sorry. What time do we have here? 2:10, perfect. And so I guess that's all we want to talk about today. We'll talk about chasing stuff in the next lecture and how you can do that, chasing or evading stuff in the next lecture. Right? If you're a little bit, if you don't remember your basic linear algebra, there is a reference book in the library. So it's called, what the heck's it called? It's a game physics book. The library has a reference to it. I will post the information on OnQ. It's got a chapter in there that talks about all of this stuff if you need to remember that.